Good day, everyone. This is digital signal processing. This is laboratory activity 4, digital signal amplitude transformations. So, here are the objectives. So, students should be able to generate discrete time signals using Python and apply amplitude transformations such as amplification, attenuation, and inversion, and also to visualize and analyze the effect of amplitude transformation on digital signals and the background. I'll read it for you. The amplitude transformation. It is the modification of signal's amplitude by applying a scaling factor or inversion, and for the amplification, increasing the signal amplitude by multiplying with a factor greater than 1. For the attenuation, decreasing the signal amplitude by multiplying with a factor between 0 and 1. And for the inversion, reversing the signal by multiplying with -1. So we need a computer with Python installed. We're going to use two libraries, the NumPy and Matplotlib. So for the procedure, first is we need to import these two libraries, the NumPy and Matplotlib. NumPy as NP and Matplotlib as PLT. So the NumPy is used for handling a numbers and signal data, and for the Matplotlib, this is used for graphing or plotting signals, waveforms, and these two statements here. This is to create a discrete time signal. So in the first line, dn is the discrete time index equals np.arrange. It goes from 0 to 19 with steps of 1. So here, the signal x is for the sine wave. This is generated using the sine functions. Next, so these two statements here creates a signal that oscillates up and down over time. So this is for plotting the original sine wave signal. Plot.stem. This is ideal for the discrete time signal. This is for the title, X and Y label, and for the grid to make it easier to see how the signal changes over time and to show the plot. So this formulas here is for plotting the amplified, attenuated, and inverted discrete time signals. So for the amplified, 2 times x, attenuated, 0.5 times x, and for the inversion, -1 minus x. So these statements here is to plot the transformed signals. This one here is for the amplified, and for the attenuated, and for the inverted signal. So I use 10 and 6 for the figure size. For the subplot, 3, 1, and 1. So the amplified signal is shown in the first plot. Same here for the second plot and the third plot for the inverted. So this starts a new figure, and this shows the amplified version of the original signal. So it is amplified because it is multiplied by 2, the height of the waves. All waves are doubled. So for the attenuated, second plot, for the title, for the plot label and grid. So this is the second subplot showing the attenuated versions of the original signal. Since it's multiplied by 0.5, the wave appears shorter, half of the original height of the original signal. So for the inverted, third subplot, and for the title and labels, this shows a inverted signal where the wave is flipped vertically or mirrored. The waves that were positive are now negative, and then we'll run the code. This is the original signal, and here it is, the three transformed signals, the amplified, the attenuated, and the inverted. You can see it virtually here that the waves from the amplified is taller than the attenuated because the height of the waves jumps at number 2 and -2. And for the attenuated, the signal were shorter because it only reaches about 0.5. And for the inverted, all the positive signals are now negative. As you can see here, the attenuated or the amplified, it almost look the same but different height of the waveforms. And for the inverted, it's like it's mirrored. So this is the original signal, and the amplified, attenuated, and inverted. So for the guide questions and for the conclusion. So in this laboratory, I was able to make a discrete time signal in Python, made amplitude modification. This includes amplification, attenuation, and inversion. The result showed that the amplification raises the signal's height, attenuation lowers it, and for the inversion, it flips vertically across the axis. So that's all for the laboratory activity 4, the digital signal amplitude transformation.